Welcome back to Science Sleep Stories. Tonight, we're embarking on a journey through the deepest mysteries that continue to perplex the brightest minds in science. These aren't simple puzzles waiting for a clever solution. They're fundamental questions about reality itself, about consciousness and existence, about the fabric of the universe and our place within it. Some of these mysteries have haunted us for decades. Others have emerged only recently, as our instruments peer deeper into the cosmos and our understanding of nature grows more sophisticated. What makes a mystery truly profound isn't just that we don't know the answer, it's that the question itself challenges our most basic assumptions about how the world works. These are the problems that keep scientists awake at night, the riddles that have consumed entire careers without yielding their secrets. And yet, paradoxically, the fact that these mysteries remain unsolved tells us something essential about the nature of knowledge itself. Science has given us extraordinary gifts. We've split the atom and mapped the human genome. We've sent probes to the edge of the solar system and peered back to the birth of the universe. We've cured diseases that once devastated populations and built machines that can think. But for all these triumphs, there remain fundamental questions about reality that continue to elude us. The philosopher Socrates once said that to know is to know that you know nothing. In many ways, modern science has vindicated his wisdom. The more we learn about the universe, the more we realize how much remains hidden from us. Tonight, we'll explore these enduring puzzles. We'll venture into the realm of consciousness, where subjective experience emerges from mere matter. We'll confront the dark sectors of the cosmos, those invisible components that make up the vast majority of everything that exists yet remain utterly mysterious. We'll grapple with the nature of time itself, with quantum paradoxes that challenge our intuitions about reality, and with the profound silence of a universe that might be teeming with life we simply cannot detect. These mysteries aren't failures of science. They're invitations to deeper understanding. Each unsolved problem represents a frontier, a boundary where human knowledge meets the unknown. And at these boundaries, remarkable things happen. New theories emerge. Unexpected connections form between seemingly unrelated fields. Revolutionary insights wait to be discovered. The history of science teaches us that today's mystery often becomes tomorrow's foundation for entirely new branches of knowledge. So settle in. Let's explore the questions that science still can't answer. The puzzles that remind us that for all our progress, we've barely scratched the surface of understanding this strange and beautiful universe we inhabit. Deep within your skull, billions of neurons fire in intricate patterns. Electrochemical signals cascade through networks of breathtaking complexity. Neurotransmitters flood across synaptic gaps. Ions flow through membrane channels. All of this, the entire symphony of neural activity, somehow gives rise to something utterly remarkable. You, the feeling of being you, the subjective experience of existing as a conscious being in the world. How does this happen? How do electrochemical processes in the brain produce the rich inner life of conscious experience? How does the firing of neurons create the sensation of seeing red, or feeling pain, or tasting chocolate? How does mere matter become aware of itself? This is what philosopher David Chalmers termed the hard problem of consciousness, and it remains one of the most profound mysteries in all of science. The hard problem stands in contrast to what Chalmers called the easy problems of consciousness. Don't let the name fool you. The easy problems are far from trivial. They include understanding how the brain processes information, how it integrates data from different senses, how attention works, how we form memories, and how we produce behavior. These are monumentally complex challenges that neuroscientists have been working on for decades. But they're easy in a specific sense. They're amenable to functional explanation. We can, in principle, explain them by describing the mechanisms involved, the neural circuits and processes that carry them out. The hard problem is different. It asks not how the brain does what it does, but why doing those things feels like anything at all. Why is there something it is like to be you? Why does your subjective experience have a qualitative character, a felt quality that philosophers call qualia? When you see a sunset, you don't just process visual information about wavelengths and intensities. You experience the deep orange glow, the way the colours seem to set the sky on fire. When you taste coffee, you don't just detect chemical compounds. You experience the rich, bitter flavour, the warmth spreading through your mouth. These subjective experiences, these qualia, seem fundamentally different from mere information processing. Consider one of the most famous thought experiments in philosophy of mind, proposed by Frank Jackson. It's called Mary's Room, and it goes like this. Mary is a brilliant neuroscientist who has spent her entire life in a black and white room. She's never seen colour, but she studied colour vision exhaustively. She knows everything there is to know about the physics of light, the biology of photoreceptors, the neuroscience of visual processing. She knows which wavelengths stimulate which cells, which neural pathways carry which signals, which brain regions process which aspects of colour perception. She has complete physical knowledge about colour vision. Now imagine that one day Mary leaves her black and white room and sees colour for the first time. She looks at a ripe tomato. What happens? Does she learn something new? It seems obvious that she does. She learns what red looks like. She gains a new kind of knowledge, not knowledge about the physical processes involved in colour vision, which she already had, but knowledge of the subjective experience of seeing red. This suggests that there's something about consciousness, about subjective experience, that can't be captured by physical descriptions alone. This is the explanatory gap, as philosopher Joseph Levine called it. There seems to be an unbridgeable gulf between our descriptions of brain processes and our understanding of conscious experience. We can describe the neural correlates of consciousness in exquisite detail. We can map which brain regions are active during which experiences. We can track the flow of information through neural networks. But all of this still seems to leave out something essential. It doesn't explain why these processes are accompanied by subjective experience. It doesn't tell us what it's like to be the system doing the processing. Some philosophers and scientists argue that this explanatory gap is merely a result of our current ignorance. They believe that as neuroscience advances, we'll eventually be able to explain consciousness in purely physical terms. Patricia Churchland, a prominent neurophilosopher, has urged scientists to simply keep doing the work. Learn the science, do the science, and see what happens. The gap might close as our understanding deepens. Others take the hard problem more seriously. Chalmers himself argues that consciousness might be a fundamental feature of reality, like space or time or mass. Just as physics posits fundamental properties that can't be explained in terms of anything more basic, perhaps consciousness is one of these irreducible fundamentals. This doesn't mean consciousness is supernatural or non-physical. It means it might be woven into the fabric of nature in ways we're only beginning to appreciate. There are radical proposals in this direction. Some theorists, like Giulio Tononi, with his integrated information theory, suggest that consciousness correlates with integrated information in any system, not just brains. If a system integrates information in the right way, it has some degree of consciousness. This would mean consciousness isn't special to biological neurons. It's a property that could, in principle, emerge in any sufficiently complex and integrated system. Others propose panpsychism, the ancient idea that consciousness is ubiquitous in nature. Perhaps even fundamental particles have some primitive form of experience. Human consciousness would then be the result of these micro-experiences combining in complex ways, much as the properties of a molecule emerge from the properties of its constituent atoms. This sounds exotic, but it's been taken seriously by some contemporary philosophers and even a few physicists. Meanwhile, neuroscience continues its methodical work of mapping the neural correlates of consciousness. Researchers use advanced brain imaging, techniques to identify which neural patterns correspond to which conscious experiences. They study what happens when consciousness is disrupted by anesthesia, or sleep, or brain damage. They investigate how information integrates across different brain regions, how attention filters and focuses awareness, how the brain constructs our unified experience of the world from myriad sensory inputs. One influential framework is the global workspace theory, developed by Bernard Bears and expanded by others. This theory proposes that consciousness arises when information becomes available to a wide range of cognitive processes. The brain contains many specialized modules that process information unconsciously. Visual processing, language production, motor control, memory retrieval. These all work in parallel, mostly outside awareness. Consciousness emerges when information enters a global workspace, a kind of central hub where it becomes available to many different systems simultaneously. This broadcasting makes the information conscious. Another major theory is integrated information theory, which we mentioned briefly. Developed by Giulio Tononi and others, this framework attempts to quantify consciousness mathematically. It proposes that consciousness corresponds to integrated information that cannot be reduced to independent parts. A system is conscious to the degree that it integrates information. This theory makes concrete predictions about which systems should be conscious, and to what degree, predictions that can potentially be tested. There's also the attention schema theory, proposed by neuroscientist Michael Graciano. This suggests that consciousness is the brain's internal model of its own attention. Just as the brain constructs models of the body's position and movement, it constructs a model of attention, of what the system is focused on and aware of. This internal model is what we experience as consciousness. It's not a perfect representation of what's actually happening in the brain, but rather a simplified, abstracted model that serves useful computational purposes. Each of these theories has strengths and weaknesses. Each explains some aspects of consciousness while leaving others mysterious. And this brings us to a deeper question about the hard problem. Is it really a scientific question at all? Or is it a confusion, a category mistake, the result of asking a question that doesn't have a meaningful answer? Some philosophers, like Daniel Dennett, argue that consciousness isn't what we think it is. Our intuitions about subjective experience, about qualia, about the special nature of consciousness are illusions. They're the result of how the brain represents information to itself, not revelations about the fundamental nature of reality. Dennett advocates a form of illusionism. Consciousness doesn't really have the mysterious properties we attribute to it. There's no explanatory gap because there's nothing to explain. Beyond the complex information processing that the brain performs, this view is controversial, to put it mildly. To many people, it seems to deny the most obvious fact about existence. Of course, consciousness is real. Of course, there's something it's like to be me. To deny this seems to deny the very ground of all experience. But Dennett and other illusionists argue that this reaction is itself part of the illusion. The brain makes consciousness seem more mysterious than it really is. Recent research has begun to explore consciousness using new experimental approaches. Scientists are developing methods to measure consciousness in patients who can't communicate, in anesthetized individuals, even potentially in other species. They're studying how consciousness might emerge in development, how it could have evolved, what its function might be. Some researchers are even exploring whether artificial systems could be conscious, and if so, how we could tell. One fascinating line of research involves altered states of consciousness. What happens to consciousness under the influence of psychedelic drugs, during deep meditation, in lucid dreams? These altered states reveal that consciousness isn't a fixed thing, but a flexible process that can be radically transformed. The sense of self can dissolve. The boundary between self and world can blur. Time can seem to stop or stretch. These experiences suggest that the unified, coherent consciousness we usually experience is actually constructed by the brain, and that construction can be modified in dramatic ways. Neuroscientists have also made progress in understanding the neural basis of anesthesia. How do anesthetic drugs eliminate consciousness? They don't simply shut down the whole brain. Instead, They seem to disrupt the integration of information across brain regions. They prevent the global broadcasting that, according to global workspace theory, creates conscious awareness. This provides evidence for theories that link consciousness to information integration. Studies of split-brain patients have also been enlightening. These are people whose corpus callosum, the large bundle of fibres connecting the brain's hemispheres, has been severed, usually to treat severe epilepsy. After the surgery, the two hemispheres can no longer directly communicate. In these patients, we can ask whether there are two separate conscious minds, one in each hemisphere. The answer seems to be yes in some respects. Each hemisphere can have its own perceptions, memories, intentions, yet the patient typically experiences themselves as a unified person. This tells us something profound about the relationship between neural organization and conscious experience, though exactly what remains debated. There's also growing interest in the evolutionary origins of consciousness. When did consciousness first emerge in the history of life? Is it unique to mammals? Do birds have it? What about fish? Insects? The fact that we can't agree on where to draw the line suggests we don't fully understand what consciousness is. Some researchers argue that consciousness must have provided some evolutionary advantage, otherwise natural selection wouldn't have preserved it. But what advantage? Simply processing information doesn't require consciousness. Computers process information without being conscious. So why did evolution produce conscious creatures like us? One possibility is that consciousness allows for flexible, intelligent behavior. A conscious organism can integrate information from multiple sources, imagine different possible futures, weigh options, and make creative decisions. It's not locked into rigid stimulus-response patterns. This flexibility might be consciousness's evolutionary payoff, but this is speculation. We're still far from understanding why consciousness evolved or what function it serves. The hard problem of consciousness remains fundamentally unsolved. We've made progress in understanding the easy problems, in mapping the neural correlates of consciousness, in developing theories that explain some aspects of conscious experience. But the core mystery persists. How and why does subjective experience arise from physical processes? Why is there something it is like to be a brain? These questions continue to challenge us, to resist our best efforts at explanation. Perhaps future advances in neuroscience will close the explanatory gap. Perhaps new theories will emerge that make consciousness less mysterious. Or perhaps consciousness will remain irreducibly puzzling, a feature of reality that we can describe and predict but never fully explain. Either way, the mystery of consciousness stands as a profound reminder of how much we still don't understand about the universe and our place in it. Look up at the night sky on a clear evening, far from city lights. You'll see thousands of stars scattered across the darkness, ancient light that has travelled across space for years or centuries to reach your eyes. It's a humbling sight, a reminder of the vastness of the cosmos and our small place within it. Those stars, those distant suns with their planets and moons and asteroids, represent everything we can directly observe in the universe. Every photon of light, every radio wave, every particle we've ever detected comes from matter like this. Matter made of atoms, of protons and neutrons and electrons, matter that emits or absorbs or scatters electromagnetic radiation, matter we can see. Here's the stunning truth. All of that, everything visible, everything we can detect with our most sophisticated instruments, everything that makes up stars and planets and galaxies and us, all of it amounts to less than 5% of the universe. The rest, the vast majority of everything that exists, is made of something else. Something we can't see, something we don't understand, something we've never directly detected in any laboratory experiment. Scientists call it dark, matter and dark energy, and together they make up approximately 95% of the universe. Dark matter accounts for about 27%, dark energy for about 68%. The remaining 5% is ordinary matter, the stuff of stars and planets and people. We live, quite literally, in a dark universe. The story of dark matter begins in the 1930s with a Swiss astronomer named Fritz Zwicky. He was studying the Coma Cluster, a massive collection of more than 1,000 galaxies bound together by gravity. Zwicky measured how fast the galaxies were moving within the cluster. He then calculated how much mass the cluster must contain to prevent those fast-moving galaxies from flying apart. The gravitational attraction of the cluster's mass needed to be strong enough to hold everything together. When Zwicky did the calculation, he found something shocking. The visible matter in the cluster, all the stars and gas he could see, wasn't nearly enough to account for the observed motions. The galaxies were moving far too fast. They should have escaped the cluster's gravitational pull long ago. Yet clearly they hadn't. The cluster was stable. This could mean only one thing. There must be additional mass in the cluster, mass he couldn't see. Dark matter. For decades, Zwicky's observation was largely ignored or explained away. But in the 1970s, American astronomer Vera Rubin provided additional compelling evidence for dark matter. She studied how individual galaxies rotate. Stars in a spiral galaxy orbit the galactic center, held in place by gravity. The closer a star is to the center, where most of the galaxy's mass is concentrated, the faster it should orbit. Stars farther out, where there's less mass below them, should orbit more slowly. This is exactly how planets in our solar system behave. Mercury orbits much faster than Neptune because it's much closer to the Sun. But when Rubin measured the orbital speeds of stars at different distances from galactic centers, she found something unexpected. Stars far from the center were orbiting just as fast as stars closer in. The rotation curves, as they're called, were flat. This made no sense if gravity only came from visible matter. It suggested that galaxies are embedded in vast halos of invisible matter, matter that extends far beyond the visible disk of the galaxy. This dark matter's gravity pulls on the outer stars, making them orbit faster than they otherwise would. Since Rubin's pioneering work, evidence for dark matter has accumulated from multiple independent sources. Gravitational lensing, for example, provides a particularly direct way to detect dark matter. Einstein's general theory of relativity tells us that mass warps space-time, and this warping bends the path of light passing near a massive object. Light from a distant galaxy passing near a galaxy cluster will be deflected by the cluster's gravity, creating distorted, stretched images of the background galaxy. By measuring this distortion, astronomers can map the distribution of mass in the cluster. When astronomers do this, they find that the mass distribution inferred from lensing doesn't match the distribution of visible matter. There's far more mass than can be accounted for by stars and gas, and remarkably, they can map where this extra mass is. It's in large halos surrounding and permeating the clusters, exactly where dark matter is predicted to be. One of the most dramatic demonstrations of dark matter's existence comes from the Bullet Cluster, actually two galaxy clusters that collided about 3.8 billion light-years from Earth. When the clusters passed through each other, their galaxies, widely separated in space, mostly just sailed past one another. The hot gas between the galaxies, however, collided and slowed down, emitting X-rays that astronomers can detect. So after the collision, the gas was in one location. But when astronomers used gravitational lensing to map where the mass was, they found something remarkable. The mass wasn't where the gas was. It had passed right through, following the galaxies. This makes perfect sense if most of the mass is dark matter, which doesn't collide with itself the way normal matter does. The dark matter halos surrounding each cluster passed through each other almost unaffected, while the normal matter gas slowed down. This is powerful evidence that dark matter really exists as a separate substance, not just a modification of gravity. So what is dark matter? If it's not made of ordinary atoms, what is it made of? This is one of the great unsolved mysteries of physics. We know some things about dark matter. It must interact via gravity, obviously, since that's how we detect it. But it appears not to interact via electromagnetism, which is why it doesn't emit, absorb, or scatter light. It's invisible. It also seems to interact very weakly, if at all, via the other fundamental forces, which is why it can pass through normal matter and itself without colliding much. Particle physicists have proposed several candidates for dark matter particles. The most popular for many years were WIMPs, weakly interacting massive particles. These are hypothetical particles that only interact via gravity and the weak nuclear force. They would have masses somewhere in the range of 10 to 1,000 times the mass of a proton. If they exist, they should be all around us. Earth is moving through a sea of dark matter as it orbits the Sun. WIMPs would be constantly streaming through us and everything around us, billions of them passing through our bodies every second without leaving a trace. For decades, physicists have been trying to detect WIMPs directly. They've built extraordinarily sensitive detectors deep underground, shielded from cosmic rays and other background radiation, waiting for the rare event when a WIMP collides with an atomic nucleus in the detector. So far, despite heroic efforts, no confirmed WIMP detection has been made. This doesn't mean WIMPs don't exist. They might just be even more weakly interacting than predicted. But the null results have led physicists to consider other possibilities. Another leading candidate is the axion, a much lighter particle originally proposed to solve a different problem in particle physics. Axions would be incredibly numerous, swarming through space in vast numbers, but individually very light and carrying very little energy. Detecting them requires different experimental approaches than detecting WIMPs, and several experiments are currently underway or planned. There are more exotic possibilities. Maybe dark matter consists of primordial black holes formed in the early universe rather than from collapsed stars. Or maybe it's made of particles that only interact with normal matter through gravity, with no other forces involved at all. Some theorists even wonder whether dark matter might be more complex than we imagine, perhaps forming its own dark sector of physics with dark atoms, dark molecules, maybe even dark stars and planets, an entire shadow universe overlapping ours but largely invisible to us. The mystery of dark matter is profound, but the mystery of dark energy is even deeper. Dark energy is stranger, more perplexing, more fundamentally challenging to our understanding of physics. The discovery of dark energy came as a complete shock. In 1998, two independent teams of astronomers were studying distant supernovae, stellar explosions that can briefly outshine entire galaxies. A particular type, called Type 1a supernovae, happens when a white dwarf star accumulates too much mass and explodes. Because the physics of these explosions is well understood, Type 1a supernovae have consistent luminosity. They're standard candles, cosmic lighthouses whose true brightness is known. By measuring how bright they appear from Earth, astronomers can determine their distance. The teams were using these supernovae to measure how the expansion of the universe has changed over cosmic time. Everyone expected to find that gravity had been slowing the expansion. The mutual gravitational attraction of all the matter in the universe should be pulling back on the expansion, causing it to decelerate. The question was how much? Would the universe eventually stop expanding and recollapse? Or would it expand forever, just more and more slowly? The answer shocked the scientific community. The expansion wasn't slowing down, it was speeding up. The universe's expansion is accelerating. This completely contradicted expectations. What could cause the expansion to accelerate? What could overcome gravity's pull and push the universe apart ever faster? The answer, or rather the name for our ignorance, is dark energy. We don't know what it is. We don't know where it comes from. We know only that it exists because we can observe its effects. Something is causing space itself to expand at an accelerating rate, and we call that something dark energy. The simplest explanation, and currently the leading theoretical candidate, is that dark energy is a cosmological constant. This is an inherent property of space itself, a baseline energy that exists even in a vacuum. Empty space, according to quantum field theory, isn't truly empty. Virtual particles constantly pop in and out of existence, borrowing energy from the vacuum and then paying it back, almost instantaneously. This vacuum energy, this energy of empty space, could manifest as a cosmological constant. Albert Einstein actually introduced the cosmological constant in 1917, though for different reasons. He was trying to construct a static model of the universe, one that neither expanded nor contracted. His equations of general relativity didn't naturally give him this, so he added a term, the cosmological constant, that would perfectly balance gravity and keep the universe static. When Edwin Hubble later discovered that the universe was actually expanding, Einstein reportedly called the cosmological constant his greatest blunder. But now it's back, though with a twist. Instead of balancing gravity to keep the universe static, the cosmological constant provides a repulsive effect that accelerates expansion. In this picture, every cubic meter of space contains a tiny amount of dark energy. As the universe expands and space increases, the total amount of dark energy increases proportionally. This provides more and more push, accelerating the expansion ever faster. The problem is that when physicists try to calculate how much vacuum energy there should be, based on quantum field theory, they get an answer that's wrong by a factor of about 10 to the power of 120. That's a one followed by 120 zeros. It's the worst prediction in the history of physics. Something is clearly very wrong with our understanding, either of quantum field theory, or of gravity, or of both. Maybe dark energy isn't a cosmological constant. Maybe it's something more dynamic, a field that changes over time, something physicists call quintessence. Maybe it's a sign that Einstein's theory of gravity needs modification on the larger scales. Maybe there are extra dimensions of space, and dark energy is related to how gravity leaks into these extra dimensions. The truth is, we simply don't know. What we do know is that dark energy is dominating the future evolution of the universe. As the universe expands and ordinary matter gets more spread out, its gravitational influence diminishes. But dark energy's effect remains constant or even grows. Over cosmic time, dark energy is winning. It's pulling the universe apart ever faster. The ultimate fate of the universe depends on dark energy. If dark energy remains constant, the universe will expand forever, accelerating all the while. Distant galaxies will recede from us faster and faster, eventually exceeding the speed of light in their recession. Not because they're moving through space faster than light, which is impossible, but because space itself is expanding between us and them faster than light can traverse it. These galaxies will disappear beyond our cosmic horizon, their light never able to reach us. The universe will become increasingly empty, cold and dark. If dark energy grows stronger over time, the outcome is even more dramatic. In a scenario called the Big Rip, dark energy's accelerating pull eventually overcomes all other forces. First, galaxy clusters are pulled apart, then galaxies themselves, then solar systems, then planets. Eventually molecules, atoms, even atomic nuclei are torn asunder as space itself is ripped apart. The universe ends not in a whimper, but in a catastrophic disintegration of matter itself. On the other hand, if dark energy diminishes over time or somehow reverses, the expansion could slow down or even reverse. Gravity could eventually win, pulling everything back together in a big crunch, the opposite of the Big Bang. The universe would collapse, growing hotter and denser, until everything merges into an infinitely dense singularity. We don't know which of these futures awaits us. We're living through a cosmic phase where dark energy is beginning to dominate, where the accelerated expansion is just becoming apparent. We're fortunate, in a sense, to live in a time when we can still observe distant galaxies, when the universe is still young and rich enough for us to study. In the far future, if dark energy remains dominant, inhabitants of the Milky Way would see a much emptier universe, most galaxies having receded beyond their horizon. The dark universe, this reality where 95% of everything is invisible and mysterious, challenges our understanding at the deepest level. It tells us that the universe is fundamentally stranger than we imagined. that the matter we're made of is a tiny minority component, that the very fabric of space harbours an energy we can't explain. These mysteries aren't minor details to be cleared up. They're massive gaps in our knowledge, fundamental puzzles about the nature of reality. Scientists are working to solve these mysteries. New telescopes, new detectors, new experiments are being designed and built. We're mapping the distribution of dark matter throughout the universe, measuring how dark energy has affected cosmic expansion over time, searching for dark matter particles in labs deep underground. Perhaps these efforts will pay off. Perhaps we'll detect a dark matter particle directly, confirming one of the theoretical candidates. Perhaps we'll make a measurement that points to the nature of dark energy, that tells us whether it's a cosmological constant or something more exotic. Or perhaps the answers will remain elusive. Perhaps dark matter and dark energy will continue to defy our efforts to understand them, continuing to shape the cosmos while hiding their true nature from us. Either way, the dark universe stands as one of the great mysteries of science, a reminder that for all our progress, we're still groping in the darkness, trying to comprehend a reality that vastly exceeds our current understanding. Time flows forward. Past becomes present, becomes future. Cause precedes effect. We age but never grow younger. We remember yesterday but not tomorrow. Broken glass doesn't spontaneously reassemble. Smoke doesn't gather itself back into solid form. These facts seem so obvious, so fundamental to our experience that we rarely question them. Yet they point to one of the deepest mysteries in physics. Why does time have a direction? Why is the past different from the future? At the most fundamental level, the laws of physics are time-symmetric. If you film a basic physical process at the quantum level and play the video backward, it would look just as physically valid as the forward version. An electron absorbing a photon looks the same as an electron emitting a photon if you reverse the direction of time. Newton's laws of motion work equally well in both time directions. Even Einstein's general relativity treats past and future on equal footing. Yet our lived experience is utterly different. We perceive a clear arrow of time pointing from past to future. We remember the past, but not the future. We can influence the future through our choices, but we can't change the past. Entropy, the measure of disorder in a system, always increases. This is the second law of thermodynamics, perhaps the most unforgiving law in all of physics. In any closed system, entropy must increase or at best stay the same. It never decreases. The second law explains why ice cubes melt in warm water, but warm water never spontaneously organizes itself into ice cubes. It explains why perfume disperses throughout a room but never gathers itself back into the bottle. It explains why we age, why machines wear out, why stars eventually exhaust their fuel. Entropy increase drives the arrow of time that we experience. But here's the puzzle. If the fundamental laws of physics are time-symmetric, where does the second law come from? Why does entropy increase? The second law is statistical, not fundamental. A low entropy state could, in principle, spontaneously arise from a high entropy state. All the air molecules in a room could by chance happen to move into one corner, leaving the rest of the room in vacuum. The laws of physics don't forbid this. It's just extraordinarily, mind-bogglingly improbable. The Austrian physicist Ludwig Boltzmann provided the statistical foundation for understanding entropy. He showed that entropy corresponds to the number of possible microscopic arrangements that give rise to the same macroscopic state. A system evolves toward higher entropy simply because there are vastly more ways to be disordered than to be ordered. High entropy states are more probable because they correspond to more possible arrangements of particles. But this raises a deeper question. Why did the universe start in a low entropy state? The Big Bang, the beginning of our universe, was a state of extremely low entropy. All the matter and energy in the universe was compressed into an infinitesimally small volume, in a highly ordered state. As the universe expanded and evolved, entropy increased. Stars formed and burned, galaxies clustered, complex structures emerged. Throughout this process, total entropy kept increasing, as the second law demands. The arrow of time points away from the Big Bang. The past is the direction of lower entropy, the future the direction of higher entropy. But why did the universe begin in such a low entropy state? This is the mystery. The Big Bang could, in principle, have started in a high entropy state. The laws of physics don't require a low entropy beginning. Yet if the universe had started with high entropy, there would be no arrow of time, no past and future, no evolution toward increasing complexity. There would be no stars, no planets, no life. The existence of observers like us depends crucially on the universe having started in a very special, very low entropy state. Some physicists, like Roger Penrose, have argued that this demands explanation. The low entropy beginning of our universe is so improbable that it can't be just a lucky accident. There must be some deeper principle, some constraint on initial conditions, that explains why the universe started this way. Penrose has proposed that this might be related to quantum gravity, to the behaviour of space-time at the Big Bang. Maybe quantum effects at the Planck scale naturally give rise to low entropy initial conditions. Others suggest that our universe might be one of many, part of a vast multiverse. In this picture, different universes start with different entropy values. Only in those rare universes that start with low entropy does an arrow of time emerge, does evolution occur, does life develop. We find ourselves in a low entropy universe for the same reason we find ourselves on a life-bearing planet. Not because such conditions are common, but because we couldn't exist anywhere else. This is an application of the anthropic principle, the idea that we should expect to find ourselves in a universe compatible with our existence. The arrow of time manifests in multiple ways beyond entropy. There's a psychological arrow, the fact that we remember the past but not the future. There's a causal arrow, the fact that causes precede their effects. There's a cosmological arrow, the expansion of the universe. And there's a quantum mechanical arrow, related to the collapse of the wave function when measurements are made. Are these different arrows related? Do they all point in the same direction for the same reason, or is their alignment a coincidence? Most physicists believe they're related, that they all ultimately stem from the thermodynamic arrow, from the increase of entropy over time, but proving this rigorously has proven difficult. The psychological arrow is particularly intriguing. Why do we remember the past but not the future? Memory formation is a physical process that creates records, structures that contain information about past events. Creating these records requires increasing entropy elsewhere. Your brain can form a memory of an event only by expending energy and generating heat, increasing the entropy of your environment. This thermodynamic cost might be why memory is directional, why we remember the past but not the future. But this raises questions about free will and determinism. If the laws of physics are time-symmetric, if the future is in principle determined by the present just as much as the past is, do we really have free will? Can we actually influence the future through our choices? Or is the feeling of free will an illusion created by our asymmetric relationship with time? The quantum mechanical arrow of time is especially puzzling. Quantum mechanics describes how systems evolve smoothly and deterministically according to the Schrödinger equation. This evolution is time-symmetric. Run it backward and you get an equally valid physical process. But when we measure a quantum system, something different happens. The wave function collapses. The system goes from being in a superposition of multiple states to being in a definite state. This collapse process is not time-symmetric. It creates an arrow of time. What causes collapse? This is one of the biggest unsolved problems in quantum mechanics, related to the famous measurement problem. Some interpretations of quantum mechanics, like the many worlds interpretation, avoid collapse by saying that all possible measurement outcomes occur in different branches of reality. In this view, there's no collapse, and the quantum mechanical arrow of time is an illusion created by our limited perspective. Other interpretations accept collapse as real, but struggle to explain what causes it and why it's directional. There's also the question of time travel. If the laws of physics are time-symmetric, does this mean travelling backward in time is possible? Einstein's general relativity allows solutions that include closed time-like curves, paths through space-time that loop back on themselves, potentially allowing travel to the past. But these solutions typically require exotic matter with negative energy density, and it's unclear whether such matter can exist. Most physicists are skeptical that backward time travel is actually possible, but we can't definitively rule it out based on our current understanding of physics. The arrow of time becomes especially puzzling at the cosmological scale. The universe is expanding, and this expansion has a direction, from past to future. But what if the universe eventually stops expanding and begins to contract? What if there's a big crunch? Would the arrow of time reverse? Would entropy decrease during the contraction phase? Most physicists think not. The thermodynamic arrow would continue to point toward the future even if the universe contracted. Entropy would keep increasing, meaning the universe would become more disordered during the collapse, not more ordered. This seems strange. The universe would be running backward in time cosmologically, shrinking instead of expanding, but forward in time thermodynamically, becoming more disordered. The different arrows of time might not be as tightly linked as we assume. Recent developments in physics have added new dimensions to the mystery of time. Quantum entanglement, for example, seems to transcend time in some ways. When particles are entangled, measuring one instantly affects the other, regardless of the distance between them. This has led some physicists to suggest that quantum correlations might not respect temporal order in the way we usually assume. Time might be more fluid at the quantum level than our everyday experience suggests. The study of quantum gravity, the attempt to merge quantum mechanics with general relativity, has also raised profound questions about time. Some approaches to quantum gravity, like loop quantum gravity, suggest that time itself might be emergent, not fundamental. At the deepest level, at the Planck scale, time might not exist at all. What we perceive as the flow of time might be a macroscopic phenomenon that emerges from something more fundamental and timeless. The physicist Carlo Rovelli has argued that time might be relational rather than absolute. There might not be a universal now, a single present moment that applies everywhere in the universe. Instead, time might be defined only by the relationships and interactions between physical systems. Different observers, in different parts of the universe or moving at different speeds, would have different notions of simultaneity, different ways of dividing events into past, present and future. All of this points to a profound mystery at the heart of physics. We experience time as flowing from past to future, as having a clear direction. Yet our best theories of fundamental physics are time-symmetric. The arrow of time, so obvious in our daily lives, seems to be absent from the deepest laws of nature. How can this be? How does a directional experience of time emerge from time-symmetric laws? The mystery of time's arrow reminds us that our intuitive understanding of reality can be deeply misleading. Time seems so obviously real, so fundamentally woven into the fabric of existence. Yet physics tells us that time might be stranger and more subtle than we imagine. It might be emergent rather than fundamental, relational rather than absolute. The flow of time, the distinction between past and future, might be features of our macroscopic world that don't apply at the deepest levels of reality. Understanding time remains one of the great challenges of physics. It connects to almost every other deep question in the field, from the nature of entropy and the origin of the universe to the interpretation of quantum mechanics and the possibility of unifying gravity with the other forces. As we continue to probe these mysteries, our understanding of time itself will likely continue to evolve, perhaps in ways that would seem as strange to us now as relativity and quantum mechanics seemed to physicists a century ago. 4 billion years ago, Earth was a harsh and alien world. The atmosphere contained no free oxygen. The oceans were filled with dissolved iron. Meteors and comets regularly bombarded the surface. Volcanic activity was widespread. The sun was dimmer than today, yet Earth was warmer, perhaps due to greenhouse gases in the atmosphere. This was the primordial Earth, and somewhere, somehow, in this hostile environment, life emerged. How? How did non-living chemistry become living biology? How did the first cell assemble itself from mere molecules? This is the origin of life, and it remains one of the deepest unsolved mysteries in science. The question can be broken into several parts. First, where did the basic building blocks come from? The amino acids and nucleotides and other organic molecules that life requires. Second, how did these building blocks assemble into more complex structures like proteins and RNA? Third, how did self-replication begin, the ability of molecules to make copies of themselves? And fourth, how did these self-replicating chemical systems eventually give rise to the first living cells, with membranes and metabolism and all the machinery of life? Let's start with the building blocks. In the 1950s, Stanley Miller and Harold Urey performed a famous experiment. They created a mixture of gases thought to resemble Earth's early atmosphere: methane, ammonia, hydrogen, and water vapour. They sealed this mixture in a flask and subjected it to electrical sparks simulating lightning. After a week, they analysed the products and found something remarkable. Amino acids had formed. The building blocks of proteins had been synthesized from simple gases and energy. The Miller-Urey experiment demonstrated that organic molecules, the chemical precursors to life, could form naturally on the early Earth. It launched the field of prebiotic chemistry, the study of chemical reactions that might have preceded life. Since then, researchers have shown that many other biologically important molecules can form under prebiotic conditions. Nucleotides, the building blocks of RNA and DNA. Lipids, the molecules that form cell membranes. Sugars, important for energy and structure. The raw materials of life can arise naturally from simple chemistry. But we now know that Earth's early atmosphere was probably not as reducing, not as rich in hydrogen, as Miller and Urey assumed. This doesn't invalidate their insight, but it means the actual pathways to organic molecules on early Earth might have been different. Perhaps organic molecules arrived from space, delivered by meteors and comets. We know that organic compounds exist throughout the solar system. Comets contain water, methane, ammonia, and complex organic molecules. Meteorites called carbonaceous chondrites contain amino acids and nucleotides. An interstellar supply of organic molecules supplementing terrestrial synthesis is entirely plausible. Once the building blocks existed, the next challenge was assembly. How do you go from a dilute soup of amino acids to proteins, from scattered nucleotides to RNA? This is harder than it sounds. In modern cells, proteins are assembled by ribosomes according to instructions encoded in RNA, which is itself assembled by enzymes, which are proteins. It's a chicken and egg problem. You need proteins to make RNA and RNA to make proteins. How did this interdependent system get started? One influential idea is the RNA world hypothesis, proposed independently by several scientists in the 1960s and given its name by Walter Gilbert in 1986. The hypothesis suggests that early life was based on RNA alone, not on the protein-RNA partnership we see today. RNA can do both jobs. It can store genetic information, like DNA, and it can catalyze chemical reactions like proteins. Some RNA molecules, called ribozymes, can even catalyze their own replication. In the RNA world scenario, life began with self-replicating RNA molecules. These molecules copied themselves, competed for resources, and evolved. Over time, they became more complex and more efficient. Eventually, they began encoding information for proteins, which could do certain jobs better than RNA. Later still, DNA evolved as a more stable molecule for long-term information storage. The RNA world gave way to the DNA-RNA protein world we see in all modern life. The RNA world hypothesis is elegant, but it faces challenges. synthesizing ribonucleotides, the building blocks of RNA, under prebiotic conditions is difficult. RNA is also chemically unstable, especially in water, which makes it a fragile foundation for early life. And while we know that some RNA molecules can catalyze reactions, we've never found or created an RNA molecule that can fully replicate itself, that can make accurate copies of arbitrary RNA sequences including its own. This is a significant gap. Some researchers have proposed alternatives or predecessors to the RNA world. Maybe life started with simpler genetic molecules that were later replaced by RNA. Candidates include TNA, PNA, and other synthetic nucleic acids. Or maybe life began with proteins or peptides, short chains of amino acids that can catalyze reactions and self-assemble into complex structures. Some scientists advocate for a metabolism-first approach, arguing that self-sustaining chemical cycles came before self-replicating molecules. The metabolism-first hypothesis focuses on chemical reactions rather than replication. Life, in this view, started with networks of chemical reactions that could maintain themselves, taking in energy and raw materials and producing more of the molecules involved in the reactions. These autocatalytic cycles didn't replicate themselves in the genetic sense. They simply sustained themselves, growing and persisting as long as resources were available. Genetic replication came later, once these metabolic systems were established. One setting where such chemistry might have occurred is hydrothermal vents on the ocean floor. These vents emit hot, mineral-rich water that mixes with cold seawater, creating chemical gradients and abundant energy. The minerals in the vent walls can catalyze reactions. The tiny pores in the minerals can concentrate molecules, providing compartments for chemistry. Some researchers argue that hydrothermal vents provided ideal conditions for the origin of life, combining energy, chemical gradients, catalysts, and compartmentalization. Nick Lane and others have developed this idea in detail. They point out that early life needed energy, and all living things today obtain energy using chemical gradients across membranes. Perhaps the first metabolic cycles used natural gradients at hydrothermal vents, gradients between acidic ocean water and alkaline vent fluid. These gradients could have driven the synthesis of organic molecules and the emergence of protometabolism. Only later did cells develop their own membranes and the machinery to create gradients themselves. But regardless of where life originated, there's still the problem of how self-replication began and how it led to evolution. Darwinian evolution requires three things: replication, variation, and selection. Entities must make copies of themselves. The copies must sometimes differ from the originals, introducing variation, and some variants must survive and reproduce better than others, leading to selection. Once you have these three ingredients, evolution is inevitable. The population will evolve, with successful variants becoming more common over time. But how did the first replicator arise? How did a molecule or system first gain the ability to make copies of itself? This is the heart of the origin of life problem. Random chemistry can make complex molecules, but true self-replication requires something more. It requires a molecule that can template its own synthesis, that can guide the assembly of a copy of itself from raw materials. One possibility is that early replicators were much simpler and less accurate than modern genetic systems. Maybe the first replicators made many errors, producing copies that were only rough approximations of the original, but even rough replication would be enough to get evolution started. Over time, variants that replicated more accurately would be selected, gradually improving the fidelity of replication. This bootstrapping process could have led from simple error-prone replication to the sophisticated genetic systems we see today. There's also the question of compartmentalization. Modern life is cellular. Every living thing we know consists of one or more cells, membrane-bound compartments that separate the internal chemistry of life from the external environment. When did cells first form? Did replication and metabolism emerge first in open environments, only later being enclosed in membranes? Or did compartmentalization come early, with the first replicators arising inside lipid vesicles or mineral pores. Compartmentalization offers important advantages. It keeps the products of reactions close together, making further reactions more likely. It allows concentrations of molecules to build up, accelerating chemistry, and it creates a unit of selection. When a vesicle contains a successful replicator, the vesicle as a whole benefits. The replicator can multiply inside the vesicle, eventually causing the vesicle to divide, spreading copies of the replicator to daughter vesicles. This is a primitive form of cellular reproduction. Remarkably, lipid vesicles can form spontaneously in water. Lipid molecules, with their water-loving and water-repelling ends, naturally assemble into bilayers and vesicles. On the early Earth, wherever lipids were present, vesicles would have formed. Some of these vesicles would have enclosed interesting chemistry by chance. If that chemistry included self-replicating molecules, you'd have a protocell, a precursor to true living cells. The progression from protocells to true cells required many innovations. Protocells needed to develop more sophisticated membranes that could regulate what entered and left the cell. They needed to evolve metabolism, chemical pathways for extracting energy from the environment, and using it to synthesize needed molecules. They needed genetic systems that could store information reliably and evolve over time. All of this had to happen before the first recognizable living cell emerged. How long did this process take? We don't know exactly. The Earth formed about 4.5 billion years ago. The oldest undisputed evidence of life dates to about 3.5 billion years ago, though some disputed evidence suggests life might have existed as early as 3.8 or even 4.1 billion years ago. This means life emerged relatively quickly, within the first billion years or less of Earth's history. Given how little we understand about the process, this rapid emergence is striking. It suggests that once conditions were right, life arose relatively easily. Or does it? Maybe we just got lucky. Maybe the origin of life is extraordinarily improbable, and we happen to live on the one planet in billions where the improbable occurred. This is the sampling bias problem. We can only observe the outcome on planets where life succeeded. Planets where life never emerged contain no observers to note their sterility. From our perspective, trapped on a single data point, we can't tell whether life's origin is easy or hard, common or rare. This matters for astrobiology, the search for life beyond Earth. If life originates easily, wherever conditions are suitable, the universe might be teeming with life. But if the origin of life requires incredibly improbable events, Earth might be one of the few life-bearing worlds in the galaxy, or even the observable universe. We simply don't know. Scientists are trying to address this question experimentally. Can we create life in the laboratory, starting from non-living materials? If we can, it would demonstrate that life's origin is possible through purely natural processes without any mysterious or miraculous intervention. It would also help us understand which conditions and which chemical pathways are most important. No one has yet created artificial life from scratch, but progress has been made. Researchers have synthesized self-replicating molecules, created artificial cells with basic metabolism, and built genetic systems from the ground up. Some have synthesized entire bacterial genomes and transplanted them into cells, creating organisms whose DNA is entirely artificial. These are important steps, but they're not the same as creating life de novo from non-living molecules. That remains beyond our current capabilities. The origin of life is uniquely challenging because it happened once, long ago, in conditions that no longer exist on Earth. We can't observe the process directly. We can only infer what might have happened based on chemistry, geology, and biology. Different researchers emphasize different aspects, leading to competing hypotheses. Some favor the RNA world, others metabolism-first approaches. Some think life started in a warm little pond, others in hydrothermal vents or on the surfaces of minerals or even in ice. The truth is we don't know which, if any, of these scenarios is correct. What we do know is that life on Earth shares a common ancestor. All living things, from bacteria to blue whales, use the same genetic code, the same basic biochemistry. This suggests that all life descended from a single origin, a last universal common ancestor that lived perhaps 4 billion years ago. If there were multiple separate origins of life on early Earth, only one lineage survived to give rise to all modern life. The others, if they existed, left no descendants. Understanding the origin of life isn't just about satisfying curiosity, it has profound implications. If we understand how life began on Earth, we can better assess the likelihood of life elsewhere. We can design experiments to search for life on other worlds, knowing what chemical signatures to look for. We might even be able to create new forms of life in the laboratory, with applications in medicine, industry and technology. The origin of life remains one of science's greatest mysteries. We've learned much about the chemistry that might have preceded life, about possible pathways from molecules to cells, but we still don't have a complete, convincing account of how life began. The transition from chemistry to biology, from non-living to living, remains poorly understood. It's a frontier of science where chemistry meets biology, meets geology, meets astrobiology, where fundamental questions about the nature of life itself remain unanswered. And until we solve this mystery, until we understand how life began, we won't fully understand what life is or what role it plays in the universe. The night sky is vast and ancient. Our Milky Way galaxy alone contains 200 to 400 billion stars. Many, perhaps most of these stars have planets. Some of those planets orbit in the habitable zone, that sweet spot where temperatures allow liquid water to exist on a planet's surface. Liquid water is thought to be essential for life, at least life as we know it. Even conservative estimates suggest billions of potentially habitable planets in our galaxy alone. And the galaxy itself is 10 billion years old, much older than our solar system's 4.6 billion years. Plenty of time for life to emerge, to evolve, to develop intelligence and technology. Scale this up to the entire observable universe with its 2 trillion galaxies, and the numbers become incomprehensible. If conditions for life are common, if intelligence is a probable outcome of evolution, then the universe should be teeming with civilizations. Some should be far older and more advanced than us. They've had billions of extra years to develop technology, to explore space, to spread across their galaxies. So where is everyone? Why do we see no evidence of other civilizations? No megastructures encasing stars to harvest their energy? No signs of planet-wide engineering projects? No artificial signals in the radio spectrum? No alien probes exploring our solar system? The cosmos appears empty, silent, devoid of other intelligences. This is the Fermi Paradox, named after physicist Enrico Fermi, who supposedly asked over lunch one day, "Where is everybody?" The paradox arises from the contradiction between high estimates for the probability of intelligent life and the complete absence of evidence for it. Given the age and size of the universe, given the abundance of potentially habitable worlds, we should expect to see aliens, yet we don't. Something in our assumptions must be wrong. Let's think about what it would take for an advanced civilization to become noticeable across interstellar distances. They don't necessarily need faster than light travel. Even moving at a fraction of the speed of light, perhaps 1%, a civilization could colonize the entire galaxy in a few tens of millions of years. They could send out spacecraft to nearby stars, establish colonies, build infrastructure. Those colonies could then send out their own spacecraft, expanding the sphere of settlement. This process would continue exponentially. 10 million years sounds like a long time, but it's short compared to the galaxy's age. If a civilization began this process even a few 100 million years ago, they should have colonized everywhere by now, including our solar system. We should see evidence of their presence, yet we don't. Why not? This is the essence of the Fermi Paradox. The galaxy is old enough that it should have been colonized many times over. The silence suggests something is preventing civilizations from spreading, from becoming obvious, from contacting us. But what? Scientists and philosophers have proposed numerous solutions to the Fermi Paradox, each with its own implications and problems. Let's explore some of the major categories of explanation. Perhaps we're alone, maybe life, or intelligent life, or technological life, is extraordinarily rare. Maybe Earth is special, perhaps uniquely so. This is the rare Earth hypothesis. It suggests that while microbial life might be common in the universe, the emergence of complex multicellular life requires such a specific set of conditions that it almost never happens. And the further step to intelligence and technology is even rarer. What might make Earth special? We orbit a G-type star, common but not too common, stable and long-lived. We're in the habitable zone. We have a large moon that stabilizes our axis and creates tides. We have plate tectonics that recycle carbon and maintain a stable climate over geological time. Our solar system has Jupiter, a giant planet whose gravity shields the inner planets from some comets and asteroids. Earth's magnetic field protects us from solar radiation. The list goes on. Each of these factors might be necessary for complex life. If so, worlds with all these features might be very rare. We might be among the few, perhaps even the only one in our galaxy. This would solve the Fermi Paradox. There's no one else because we're alone. But this explanation is uncomfortable. It requires Earth to be special, to be the result of an unlikely combination of circumstances. In the history of science, we've repeatedly learned that Earth and humanity are not privileged. We're not at the centre of the universe. Our sun is an ordinary star. Our galaxy is one of billions. Why should our planet be the unique exception? The one place where complex life emerged? Another category of explanation invokes the Great Filter. This is the idea that somewhere in the progression from non-life to galaxy-spanning civilization, there's a step that's extremely difficult or even impossible to pass. A filter that strains out almost all civilizations. The question is where the filter is. If the filter is behind us, perhaps at the origin of life, or the evolution of complex cells, then we're among the few who made it through. This would explain why we don't see other advanced civilizations. Most never get past the filter. This scenario is actually optimistic for our future. If we've already passed the hardest step, we might have a good chance of surviving and spreading. But if the filter is ahead of us, the implications are grim. Maybe there's something about technological civilizations that causes them to self-destruct. Nuclear, war, climate change, engineered pandemics, artificial intelligence gone wrong, or some danger we haven't even imagined yet. In this scenario, the reason we don't see other civilizations is that they don't last long. They reach a certain level of technology and then destroy themselves. And if that's the case, the same fate likely awaits us. We have no way to know where the filter is, which makes the Great Filter hypothesis both powerful and unsettling. It explains the Fermi Paradox, but leaves us uncertain about humanity's future. Every year we survive as a technological civilization without destroying ourselves is in a sense good news. It suggests that maybe the filter is behind us after all. Perhaps civilizations don't want to spread. Maybe the assumption that intelligent species will colonize space is wrong. Maybe the drive to explore and settle is a specifically human trait, not a universal feature of intelligent life. Or maybe advanced civilizations do spread, but in ways we don't recognize. They might expand into virtual realities rather than physical space, building complex simulations rather than traveling to other stars. From our perspective, they would appear to stop expanding, to go quiet when in fact they've simply moved into domains we can't observe. Or maybe civilizations are out there but deliberately hiding from us. This is the zoo hypothesis. Perhaps there's a galactic club, a federation of advanced species, that has a policy of non-interference with younger civilizations. They're aware of us but choosing not to contact us, letting us develop naturally until we reach some threshold. Earth is a zoo, an anthropological study, quarantined for our own development. This sounds like science fiction, and critics point out that it requires all civilizations to cooperate in the quarantine. It would only take one rogue civilization, one alien species that decides to say hello, to break the silence. The fact that no one has suggested that if the zoo hypothesis is correct, the quarantine is perfectly enforced, which seems unlikely. Perhaps the problem is communication. We've only been listening for alien signals since 1960, just over 60 years. That's a blink of an eye on cosmic timescales. Moreover, we've only searched a tiny fraction of the sky, at limited frequencies, with limited sensitivity. Maybe civilizations are broadcasting, but we haven't yet developed the technology to detect their signals, or we're not looking in the right places. Radio waves travel at the speed of light. The signals we've sent into space, our television and radio broadcasts, have only reached stars within about 60 light years. Even if aliens nearby received our signals and immediately replied, we wouldn't hear their response for decades or centuries. The vastness of space creates immense time delays in any interstellar conversation. Moreover, advanced civilizations might not use radio. They might communicate using methods we can't detect or haven't thought of. Neutrinos, gravitational waves, modulated laser pulses, encrypted quantum channels, or entirely different physics we don't yet understand. We might be surrounded by alien communications but unable to recognize them, like a dog watching television with no comprehension of what the flickering images represent. There's also the possibility that civilizations arise at different times, separated by billions of years. The galaxy might have hosted intelligent life in the past, and it might host it in the future, but right now we're alone. The cosmic equivalent of ships passing in the night, civilizations existing at different epochs, never overlapping in time, or perhaps spacefaring civilizations don't last long for economic rather than catastrophic reasons. Interstellar colonization might simply be too expensive, too difficult, with too little payoff. Why send ships to other stars when you can build comfortable habitats in your own solar system, or upload yourself into computers, or genetically engineer yourself to thrive in any environment? The assumption that advanced civilizations want to expand might be wrong. Some solutions to the Fermi Paradox are more exotic. Perhaps we're living in a simulation, and the simulators haven't bothered to simulate other civilizations. Perhaps the laws of physics make interstellar travel impossible in ways we don't yet understand. Perhaps consciousness is rare, arising only under specific conditions that Earth happens to meet. Perhaps intelligence is common, but technology is rare, most intelligent species never developing beyond stone tools. The dark forest hypothesis, popularized by science fiction author Lou Sixin, proposes a chilling solution. Perhaps the galaxy is full of civilizations, but they're all hiding. Any civilization that reveals itself becomes a target. In a universe where resources are finite and intentions are unknowable, the safest strategy is to stay silent and eliminate any other civilization you detect before they can eliminate you. The galaxy is a dark forest, and we're all hunters and prey at once. Under this hypothesis, our broadcasts announcing our presence to the cosmos might be the most dangerous thing humanity has ever done. Recent research has added new dimensions to the paradox. The discovery of thousands of exoplanets since the 1990s has confirmed that planets are common, including planets in habitable zones. This strengthens one side of the paradox. Potential habitats for life are abundant, yet the silence remains. The more planets we find, the more puzzling it becomes that we see no signs of life. Some scientists have proposed that we might not recognize alien intelligence if we saw it. Our conception of intelligence and technology is anthropocentric, based on our own experience. Alien minds might think in completely different ways, value completely different things, use completely different technologies. They might not build radio transmitters or megastructures. They might not explore space. They might not even be based on solid matter, instead existing as coherent electromagnetic phenomena or as information patterns in some substrate we can't imagine. The cognitive horizon hypothesis, recently proposed, suggests that human cognition has limits. Just as a dog can't understand quantum mechanics no matter how much training it receives, humans might be constitutionally incapable of recognizing or understanding certain forms of intelligence or phenomena. Alien civilizations might be all around us, but we can't perceive them because they're beyond our cognitive horizon. The search for extraterrestrial intelligence continues. SETI, the search for extraterrestrial intelligence, has been scanning the skies for artificial signals for over 60 years. New initiatives like Breakthrough Listen are using more sensitive instruments to search more of the sky more thoroughly. We're developing methods to search for technosignatures, signs of alien technology, in addition to biosignatures, signs of life. We're getting better at characterizing exoplanet atmospheres, looking for chemical imbalances that might indicate biological activity. Maybe we'll find evidence of life someday. Maybe we'll detect a signal or observe an exoplanet with an atmosphere wildly out of chemical equilibrium, or spot a megastructure. That would transform our understanding of our place in the universe. We'd know we're not alone, that life and intelligence can emerge elsewhere. Humanity would become part of a larger cosmic community, even if communication takes centuries. Or maybe we'll never find evidence of other civilizations. Maybe we're alone, or functionally alone, separated from other intelligences by vast gulfs of space and time. That would be lonely, but also significant. It would mean that life, consciousness and intelligence are precious and perhaps unique. Our extinction would mean the loss of something irreplaceable, the only place in the cosmos where matter woke up and began contemplating its own existence. The Fermi Paradox reminds us how much we don't know about life's place in the universe. We don't know how common life is, how often it becomes complex, whether intelligence is inevitable or unlikely. We don't know whether civilizations typically destroy themselves or spread among the stars. We don't even know for certain that we're searching in the right ways or asking the right questions. The paradox is a mirror reflecting our ignorance, a reminder that despite our scientific progress, we remain profoundly uncertain about fundamental questions regarding life, intelligence, and our cosmic context. Quantum mechanics is the most successful scientific theory in history. Its predictions have been confirmed to extraordinary precision. It underpins modern technology from lasers to computer chips to MRI machines. Without quantum mechanics, chemistry would be incomprehensible. The periodic table a mystery, the behaviour of materials inexplicable. Yet for all its success, quantum mechanics harbours a deep conceptual mystery that has troubled physicists since the theory's inception. The measurement problem. To understand the measurement problem, we need to grasp the strange nature of quantum superposition. In classical physics, objects have definite properties at all times. A coin is either heads or tails. A particle is either here or there. But quantum mechanics says that before measurement, a quantum system exists in a superposition, a combination of multiple states simultaneously. An electron can be in a superposition of being spin up and spin down. A photon can be in a superposition of passing through two different slits. The particle doesn't have a definite property. It's in multiple states at once. This is profoundly weird, but it gets weirder. When you measure the system, the superposition collapses. The particle suddenly has a definite property. The electron is either spin up or spin down. The photon went through one slit or the other. Measurement forces the quantum system to choose a definite state. But what counts as a measurement? What causes collapse? This is the measurement problem. The equations of quantum mechanics, specifically the Schrödinger equation, describe how quantum systems evolve over time. This evolution is smooth, deterministic, and reversible. A superposition evolves into a different superposition. There's no collapse in the equations. Collapse is something added to the theory by hand, an additional postulate that seems inconsistent with the rest of the mathematical framework. Erwin Schrödinger, one of the founders of quantum mechanics, illustrated the paradox with his famous thought experiment about a cat. Imagine a cat sealed in a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter detects it and triggers a mechanism that breaks the vial, releasing the poison and killing the cat. The atom, being quantum, is in a superposition of decayed and not decayed until observed. According to quantum mechanics, this means the cat is also in a superposition of alive and dead until someone opens the box and looks. The cat is neither definitely alive nor definitely dead. It's in both states simultaneously. Only when observed does the superposition collapse, and the cat becomes definitely alive or definitely dead. This is absurd. Cats aren't in superpositions. They're either alive or dead. Yet quantum mechanics seems to predict superposed cats. The measurement problem is the question of when and how superpositions become definite outcomes. What makes an observation an observation? When does collapse occur? Is it when a conscious observer looks? When a measuring device records a result? When a photon from the system enters your eye? Where's the boundary between the quantum realm of superpositions and the classical realm of definite properties? Different interpretations of quantum mechanics answer these questions differently. The Copenhagen interpretation, historically dominant, says that measurement causes collapse, but it doesn't specify what counts as a measurement. It treats measurement as primitive, not further analysed. The quantum world of superpositions and the classical world of definite outcomes are separate domains with different rules. This pragmatic approach works for calculating predictions, but offers little insight into what's really happening. The many worlds interpretation, proposed by Hugh Everett in 1957, eliminates collapse entirely. When a measurement occurs, the universe splits into multiple branches. In one branch, the electron is spin-up. In another, it's spin-down. Both outcomes occur, just in different branches of reality. There's no collapse because all possible outcomes actually happen. We experience definite outcomes because we're stuck in one branch, unable to observe the others. Many worlds is elegant mathematically. It takes the Schrödinger equation seriously, allowing quantum superpositions to continue indefinitely without collapse. But it implies an enormous, perhaps infinite number of parallel universes constantly branching off from each other. Every quantum measurement creates new worlds. This profligate ontology troubles many physicists. Are all these worlds real? How can we ever test the existence of branches we can't observe? The pilot wave or de Broglie-Bohm interpretation takes a different approach. It says particles always have definite positions, guided by a pilot wave that evolves according to the Schrödinger equation. Measurements reveal pre-existing properties rather than creating them. There's no collapse because there are no true superpositions. Particles are always somewhere definite. The appearance of superposition arises from our ignorance of the precise positions. This interpretation is appealing because it restores a kind of classical reality. Particles have trajectories. They move continuously through space, but it requires accepting the pilot wave, an entity that guides particles but is never directly observed. It also implies non-locality, instantaneous influences across space, which conflicts with the spirit if not the letter of relativity. Objective collapse theories propose that collapse is real and spontaneous, not caused by observation. Quantum systems naturally collapse to definite states, with the collapse happening spontaneously at a rate that increases with the system size. For microscopic systems like single electrons, collapse is so rare that superpositions last long enough to be observed in experiments. For macroscopic systems like cats, collapse happens almost instantly, preventing superpositions of large objects. The GRW theory, named after Ghirardi, Rimini and Weber, is the most developed objective collapse model. It modifies the Schrödinger equation to include spontaneous collapse. This makes testable predictions that differ slightly from standard quantum mechanics. So far, experiments haven't detected these differences, but more sensitive tests are ongoing. Some physicists take a more radical view. Perhaps there's no measurement problem at all because there are no measurements. The quantum state doesn't describe an objective reality, but rather our knowledge or information about a system. Measurement doesn't change the system, but updates our information about it. This is the quantum Bayesian or cubism interpretation. It treats quantum mechanics as a tool for making predictions about experiences rather than a description of an independent reality. Cubism resolves the measurement problem by denying that anything physical changes when measurement occurs. Your subjective experience changes as you gain information, but the world itself continues evolving according to the Schrödinger equation. This solves the conceptual puzzle but raises questions about the nature of reality. If quantum mechanics only describes experiences, what is the underlying reality? Recent research has explored the measurement problem experimentally. Quantum computers operate by maintaining superpositions of many quantum bits, qubits, simultaneously. Understanding and controlling quantum superposition is essential for building these machines. Decoherence, the process by which quantum systems lose their superposition when interacting with their environment, is a major obstacle. By studying decoherence, scientists are learning more about the boundary between quantum and classical behaviour. Entanglement, another quantum phenomenon, is closely related to the measurement problem. When particles are entangled, measuring one instantly affects the other, regardless of distance. Einstein called this spooky action at a distance, and considered it evidence that quantum mechanics was incomplete. But experiments have repeatedly confirmed entanglement. It's real. Particles can be correlated in ways that seem impossible, according to classical physics. Entanglement deepens the measurement problem. When you measure one particle of an entangled pair, does the other particle's state collapse instantly? If so, information seems to travel faster than light. If not, how do we explain the correlations? Different interpretations answer differently. Many worlds says both particles are in superpositions that become correlated across branches. Pilot wave theory says the non-local pilot wave coordinates the particle's behaviour. The measurement problem and the interpretation of entanglement are inseparably linked. The measurement problem matters beyond philosophy. As we build quantum technologies, we need to understand when and why quantum effects persist and when they disappear. For quantum computers to work, we need to maintain superpositions. For quantum cryptography, we need to understand when measurements occur. The practical questions push us to confront the conceptual ones. Some physicists hope that quantum gravity, a theory unifying quantum mechanics with general relativity, will solve the measurement problem. Maybe at the Planck scale, the scale where quantum effects and gravitational effects both matter, something happens that causes collapse. Or maybe the measurement problem will dissolve when we properly understand how quantum mechanics applies to space-time itself. Others think the solution lies in understanding consciousness. Perhaps consciousness plays a special role in causing collapse. This was proposed by Eugene Wigner and John von Neumann, two pioneers of quantum theory. The idea is that only conscious observation causes superpositions to collapse. This would explain why laboratory instruments don't collapse quantum states until a conscious person reads them. But it raises more questions than it answers. What counts as conscious? Do animals collapse wave functions? Does a thermostat? At what point in evolution did consciousness emerge and start collapsing quantum states? The measurement problem remains unsolved nearly a century after quantum mechanics was formulated. We have no consensus on what measurement means, when collapse occurs, or whether collapse is even real. This doesn't affect quantum mechanics' practical success. The equations work regardless of interpretation. But it leaves a conceptual gap at the heart of our most fundamental physical theory. We can predict what quantum systems will do with extraordinary precision, yet we don't understand what's happening when we observe them. This mystery reminds us that science can make accurate predictions without complete understanding. We can use quantum mechanics to build technologies without agreeing on what quantum mechanics means. But the measurement problem also suggests that our understanding is incomplete, that some deeper theory awaits discovery. Whether that theory will be a refinement of quantum mechanics, a radically new framework, or simply a clearer interpretation of what we already know remains to be seen. For now, The quantum measurement problem stands as one of the deepest unresolved puzzles in physics, a reminder that even our most successful theories harbour mysteries at their core. Every night you do something strange. You lie down, close your eyes, and spend roughly 8 hours unconscious. Your body continues functioning, your heart beats, you breathe, your brain remains active. But your conscious awareness disappears. You're vulnerable, unaware of your surroundings, unable to respond to threats. From an evolutionary perspective, sleep seems like a terrible idea. Why would natural selection favour a behaviour that leaves organisms helpless for a third of their lives? Yet sleep is universal among animals with nervous systems. Fish sleep, birds sleep, mammals sleep. Even insects and worms show sleep-like states. Sleep is so fundamental that depriving animals of it has severe consequences. Prolonged sleep deprivation leads to cognitive impairment, emotional disturbances, hallucinations, and, eventually, death. Sleep isn't optional, it's a biological necessity. But why? What does sleep do that's so important it's worth the enormous risk and cost? This is one of the deepest mysteries in biology. We still don't fully understand why we sleep. Multiple hypotheses exist, each supported by some evidence, but none fully explaining sleep's necessity. Sleep likely serves multiple functions, evolved for different reasons in different lineages, and modern sleep is the result of various purposes combined. One prominent theory is that sleep allows the brain to consolidate memories. During wakefulness, you experience and learn constantly. Your brain encodes these experiences as temporary memory traces. During sleep, these traces are strengthened and integrated into long-term memory. Studies show that people perform better on memory tests after a night's sleep than after an equivalent period awake. Sleep deprivation impairs memory formation and recall. Different sleep stages appear to serve different memory functions. Slow-wave sleep, the deep sleep stage characterized by large synchronized brain waves, seems particularly important for consolidating declarative memories, memories of facts and events. REM sleep, the stage where most dreaming occurs, appears crucial for procedural memories, memories of skills and procedures. Your brain rehearses and refines what you've learned while you sleep, transforming fragile new memories into stable, lasting ones. But memory consolidation can't be the whole story. Animals with minimal cognitive abilities still sleep. C. elegans, a tiny worm with just 302 neurons, has sleep-like states. It's hard to imagine that memory consolidation is crucial for such a simple organism. If sleep evolved initially for memory, its origins must predate complex cognition. Another theory is that sleep allows the brain to clear metabolic waste. Brain activity generates toxic byproducts that accumulate during wakefulness. One such compound is beta amyloid, a protein associated with Alzheimer's disease. The glymphatic system, a network of channels that flushes waste from the brain, is much more active during sleep. Cerebrospinal fluid flows through the brain tissue, washing away accumulated toxins. This cleansing might be why sleep deprivation is associated with cognitive decline, and why chronic sleep problems correlate with increased dementia risk. The waste clearance theory is appealing because it applies broadly. Any nervous system that generates metabolic byproducts would benefit from a mechanism to remove them. Sleep could have evolved as a housekeeping function, a time when the brain's maintenance systems operate most efficiently. But this still doesn't fully explain why we must lose consciousness. Why can't the brain clean itself while we remain aware? Energy conservation is another proposed function of sleep. Being awake and alert is metabolically expensive, especially for warm-blooded animals. Sleep reduces energy expenditure, allowing organisms to conserve resources. This is particularly important for small animals with high metabolic rates, which might starve if they remained active continuously. Sleep allows them to survive periods when foraging would be inefficient or dangerous. But the energy savings from sleep are modest, maybe 10 or 20% of daily energy expenditure. This hardly seems worth the enormous risks of prolonged unconsciousness. and the energy conservation theory struggles to explain the complexity of sleep, the multiple stages with different brain activity patterns. If sleep were purely about saving energy, we'd expect simple inactivity, not the elaborate neurological choreography that actually occurs. Perhaps sleep serves immune function. During sleep, the immune system operates more effectively. Cytokines, proteins involved in immune responses, are produced at higher rates during sleep. People who sleep poorly are more susceptible to infections. Sleep deprivation impairs immune function, reducing the body's ability to fight pathogens. The link between sleep and immunity might explain why we feel sleepy when sick. The body prioritizes sleep to enhance immune defenses. Sleep might also be crucial for development. Infants and children sleep far more than adults, and much of that sleep is REM sleep. During development, the brain undergoes massive reorganization, forming and pruning synaptic connections. Sleep might provide protected time for these processes, allowing the developing brain to wire itself properly. Disrupted sleep during childhood is associated with developmental problems, suggesting sleep plays an important role in normal maturation. There's also the synaptic homeostasis hypothesis, which proposes that sleep allows the brain to downscale synaptic connections that have strengthened during the day. During wakefulness, learning and experience strengthen synapses, but if synapses only strengthened, the brain would become saturated, unable to form new memories. Sleep might reset the system, weakening synapses globally so that important connections can be strengthened again the next day. This would explain why sleep is restorative, why we wake feeling mentally refreshed. Each of these theories has experimental support, but none explains everything about sleep. The truth is likely that sleep serves multiple functions simultaneously, and these functions might differ across species and developmental stages. Sleep is ancient, predating the evolution of complex brains. Simple organisms' sleep-like states suggest that sleep's origins lie in fundamental cellular or metabolic processes. As brains became more complex, sleep was co-opted for additional functions like memory consolidation and waste clearance. The structure of sleep is itself mysterious. Why do we cycle through different sleep stages? Humans typically experience several 90-minute cycles each night, moving from light sleep to deep, slow-wave sleep to REM, sleep and back. Each stage has characteristic brain activity patterns and likely serves different functions. But why this particular cycling pattern? What would go wrong if we only had one continuous type of sleep? REM sleep is particularly enigmatic. During REM, the brain is highly active, almost as active as during wakefulness, yet the body is paralyzed. Most dreams occur during REM sleep, though we can dream in other stages too. REM sleep increases after periods of learning, suggesting it's important for memory or skill consolidation. But the paralysis is key. Without it, we'd act out our dreams, potentially injuring ourselves. The fact that evolution preserved a mechanism to paralyze us during this highly active brain state suggests REM sleep serves a critical function. One speculative idea is that REM sleep allows the brain to generate internal models of the world, to simulate scenarios without sensory input. During waking life, our experience is constrained by reality, by what actually happens. During REM, freed from sensory input and motor output, the brain can explore possibilities, strengthen connections, rehearse behaviours. Dreams might be the subjective experience of this process, the brain testing and consolidating its internal models. Another mystery is individual variation in sleep needs. Most adults need 7 to 9 hours of sleep per night, but some function well on much less. A handful of genetic mutations have been identified that reduce sleep need without apparent negative consequences. The people with these mutations sleep 5 or 6 hours and wake feeling rested. How do they differ? What aspects of sleep are they skipping? Understanding these variations might reveal which functions of sleep are truly essential and which are optional. Sleep disorders provide additional clues. Insomnia, sleep apnea, narcolepsy, restless leg syndrome. Each reveals something about sleep's mechanisms and importance. People with narcolepsy experience sudden, uncontrollable sleep attacks, entering REM sleep directly from wakefulness. This shows that REM sleep is actively generated by specific brain circuits, not simply a passive state. Sleep apnea, where breathing repeatedly stops during sleep, demonstrates the dangers of disrupted sleep. Chronic apnea is associated with cognitive decline, cardiovascular problems, and increased mortality. The sleep patterns of different species are fascinating. Dolphins and whales sleep with only half their brain at a time, allowing them to maintain some awareness while sleeping. This unihemispheric sleep lets them surface to breathe and watch for predators even while asleep. Birds can do this too, especially during migration. Some birds sleep while flying, shutting down one hemisphere and keeping the other awake to navigate. Giraffes sleep less than 2 hours per day, in short naps of a few minutes. Bats sleep up to 20 hours. Why such variation? Body size, diet, predation risk, and ecological niche all influence sleep duration and structure. But the basic phenomenon of sleep remains. Every species studied shows some form of sleep-like state, suggesting that sleep fulfills fundamentally important biological functions. One of the most profound aspects of sleep is its relationship with consciousness. When we sleep, especially in deep, slow-wave sleep, we're effectively unconscious. We don't respond to moderate stimuli. We're not aware of our surroundings, yet our brain is active, generating the slow, synchronized waves that characterize deep sleep. What happens to consciousness during sleep? Does it disappear? Is it present but without content, a kind of blank awareness? Do we always dream but simply forget most dreams upon waking? These questions connect to the broader mystery of consciousness. If consciousness is generated by neural activity, why does the active brain during sleep not produce the same rich conscious experience as the active brain during wakefulness? What's different about sleep brain activity that makes it unconscious? Understanding sleep might provide crucial insights into the nature of consciousness itself. The mystery of sleep reminds us that even familiar phenomena can hide deep puzzles. We spend a third of our lives asleep, yet we don't understand why. Sleep is clearly essential. Depriving organisms of sleep causes severe problems, but the mechanisms and functions of sleep remain incompletely understood. As neuroscience advances, as we develop better tools for monitoring and manipulating brain activity during sleep, we're gradually uncovering sleep's secrets. But the full picture remains elusive, and sleep continues to be one of biology's most intriguing unsolved mysteries. General relativity and quantum mechanics are the two foundational theories of modern physics. General relativity describes gravity, the force that shapes the universe on the larger scales. Quantum mechanics describes the behavior of matter and energy on the smaller scales. Both theories are extraordinarily successful, tested to high precision, confirmed by countless experiments. Yet they're fundamentally incompatible. This incompatibility creates a profound problem. At ordinary scales, we can use general relativity to describe gravity and quantum mechanics to describe everything else, and the two theories never need to talk to each other. But in extreme environments, both gravity and quantum effects become important simultaneously. In the first moments after the Big Bang, the entire universe was compressed to a point. Near black hole singularities, matter is compressed to infinite density. At the Planck scale, the smallest scale of distance and time, quantum fluctuations of space-time itself become important. In these regimes, we need a theory that unifies general relativity and quantum mechanics, a theory of quantum gravity. We don't have one. Despite decades of effort by some of the world's most brilliant physicists, quantum gravity remains elusive. This is one of the deepest unsolved problems in fundamental physics. The conflict between general relativity and quantum mechanics runs deep. In general relativity, space-time is smooth and continuous. It's a four-dimensional fabric that curves in response to matter and energy. This curvature is what we experience as gravity. Mass tells space-time how to curve, and curved space-time tells matter how to move. The theory is deterministic. Given initial conditions, the evolution of space-time is precisely determined. Quantum mechanics paints a very different picture. At small scales, everything is quantized, coming in discrete units. Energy, momentum, angular momentum, all exist in specific quantum states. Particles don't have definite positions until measured. The theory is inherently probabilistic. We can only calculate probabilities for different outcomes, not predict exactly what will happen. These differences make unifying the theories challenging. Should space-time be quantized? Are there fundamental units of space and time, or is space-time continuous all the way down? How do we make sense of quantum superpositions of different space-time geometries? What does it mean for space-time itself to be in a superposition? The most popular approach to quantum gravity is string theory. String theory proposes that the fundamental constituents of reality aren't point particles but tiny, one-dimensional strings. These strings vibrate in different modes, and each mode of vibration corresponds to a different particle. An electron is one vibrational mode, a quark another, a photon yet another. Gravity, in string theory, arises from a particular vibrational mode called the graviton. String theory naturally incorporates gravity. The mathematics of strings automatically includes the graviton, making gravity an integral part of the theory rather than something added on. This is string theory's great achievement. It potentially provides a unified description of all forces and particles, including gravity, within a single mathematical framework. But string theory has problems. To be consistent, strings must vibrate in 10 dimensions, not the 4 dimensions of space-time we experience. Where are the extra 6 dimensions? String theorists propose they're curled up at tiny scales, too small to be observed directly. The particular way these dimensions are curled determines the particles and forces we see in our 4-dimensional world. The problem is that there are many, possibly infinitely many ways to curl up the extra dimensions. Each way gives a different 4-dimensional physics. This is the string theory landscape, a vast space of possible universes with different particles, forces, and physical constants. Our universe corresponds to one point in this landscape, but string theory doesn't predict which point. It doesn't tell us why our universe has the properties it does, rather than some other set of properties. This makes string theory hard to test. It doesn't make specific predictions about phenomena we can observe with current technology. The characteristic scale of string theory is the Planck length, about 10 to the minus 35 meters, far beyond the reach of any conceivable experiment. Without testable predictions, it's difficult to confirm or refute the theory. Another approach to quantum gravity is loop quantum gravity. This theory takes a different starting point. Instead of trying to quantize matter and fit gravity in, loop quantum gravity tries to quantize space-time itself. It applies quantum mechanics directly to the geometry of space-time, following the principles of general relativity as closely as possible. In loop quantum gravity, space-time is not continuous at the smaller scales. It has a discrete granular structure, a kind of quantum space-time foam made of tiny loops and nodes. These loops are excitations of the gravitational field, quantum states of geometry. Space and time emerge from these discrete quantum building blocks, just as a smooth surface emerges from many small pixels. Loop quantum gravity predicts that the Big Bang singularity disappears. Instead of the universe beginning from an infinitely dense point, it might have bounced from a previous contracting phase. Singularities inside black holes might also be eliminated, replaced by quantum effects that prevent infinite densities. These are testable predictions, though testing them directly is extremely difficult. Like string theory, loop quantum gravity faces challenges. It's been difficult to show that the smooth space-time of general relativity emerges from the discrete quantum structure in the right way. The theory also struggles to incorporate matter and the other forces naturally. It's primarily a theory of quantum gravity, not a unified theory of everything. Other approaches exist. Causal set theory proposes that spacetime is fundamentally a discrete set of events with causal relationships. Asymptotic safety suggests that quantum gravity might be a well-defined quantum field theory after all, with the right mathematical structure at high energies. Emergent gravity proposals suggest that spacetime and gravity aren't fundamental, but arise from more basic quantum degrees of freedom, perhaps related to quantum information or entanglement. The lack of a successful theory of quantum gravity has profound implications. We can't fully understand the Big Bang, the first moments of the universe's existence. We can't describe what happens at the centre of black holes. We can't predict what quantum gravitational effects might occur at high energies, potentially accessible to future particle accelerators or astronomical observations. Quantum gravity also relates to other mysteries. What is the nature of time? General relativity treats time as part of space-time, intimately linked with space. But quantum mechanics assumes a universal time parameter. In quantum gravity, time itself might be an emergent concept, not fundamental. Understanding quantum gravity might require rethinking what time is. Another connection is to the information paradox of black holes. Stephen Hawking showed that black holes emit radiation, Hawking radiation, and eventually evaporate. But this seems to violate quantum mechanics. The radiation is thermal, carrying no information about what fell into the black hole. Yet quantum mechanics says information can't be destroyed. This is the black hole information paradox, and resolving it likely requires understanding quantum gravity. Recent work has focused on the relationship between quantum entanglement and spacetime geometry. There are hints that entanglement, the quantum correlation between particles, might be related to the structure of spacetime itself. In a slogan, spacetime is quantum entanglement. If true, this would represent a profound shift in how we think about reality, with spacetime not being fundamental but emerging from quantum information. The AD-CFT correspondence, a duality discovered in string theory, has provided insights into this relationship. It shows that a theory of quantum gravity in a certain type of spacetime is mathematically equivalent to a quantum field theory without gravity in one fewer dimension. This is surprising and powerful. It lets physicists study quantum gravity by studying a simpler theory without gravity. Many recent advances in understanding quantum information, black holes, and the emergence of spacetime have come from exploring this correspondence. But the AD-CFT correspondence applies to a universe with a negative cosmological constant, a shape of spacetime unlike our own. Our universe has a positive cosmological constant, which is related to dark energy and causes the universe's expansion to accelerate. Whether a similar correspondence exists for our universe remains unknown. The quest for quantum gravity continues. Physicists are exploring multiple approaches, testing different ideas, looking for mathematical consistency and physical insight. Progress is slow because we lack experimental guidance. The energies where quantum gravity becomes important are so high, the scale so small, that we can't probe them directly with current technology. But there are opportunities. Gravitational waves, ripples in space-time detected by LIGO and other observatories, might carry signatures of quantum gravity. The cosmic microwave background, the afterglow of the Big Bang, might show imprints of quantum gravitational effects from the universe's earliest moments. Future telescopes and detectors might find evidence that points the way toward the correct theory. The problem of quantum gravity is more than a technical challenge. It's a fundamental puzzle about the nature of space, time, matter, and energy. Solving it will require deep insights, perhaps even a revolution in how we think about physics. The unified theory we seek might be so different from our current theories that recognizing it when we find it will be difficult, but finding it would represent one of the greatest intellectual achievements in human history, a final understanding of how the universe works at the most fundamental level. You're reading these words by choice, at least that's how it feels. You decided to listen to this video. You could pause it or skip ahead. These seem like free choices, decisions you make autonomously. Your sense of agency, of being the author of your actions, is among the most fundamental aspects of conscious experience. Yet modern science suggests this sense of agency might be an illusion. Physics describes the universe as a deterministic system, or at best a probabilistic one where randomness, not choice, breaks the chain of causation. Neuroscience shows that brain activity precedes conscious awareness of decisions, suggesting our choices are determined by neural processes we don't control. If the physical world, including our brains, operates according to deterministic laws, where does free will fit in? Do we actually have the freedom to choose, or are our actions predetermined by prior causes stretching back to the Big Bang? This is the problem of free will and determinism, and it's one of the oldest and deepest puzzles at the intersection of philosophy, neuroscience, and physics. The question matters not just academically, but practically. Our concepts of moral responsibility, praise and blame, legal punishment and reward all depend on the assumption that people have free will, that they could have chosen differently. If that assumption is wrong, if free will is an illusion, the implications are profound. Let's start with the physics. Classical physics, the physics of Newton and Einstein, is deterministic. Given the complete state of the universe at one moment and the laws of physics, you can in principle calculate the state at any future time. The future is determined by the past. Every event, including every thought and decision you have, is the inevitable consequence of prior events. This doesn't mean we can actually predict everything. The universe is too complicated. We can't measure the initial conditions precisely enough, and the equations are too complex to solve for realistic systems. But in principle, determinism means the future is fixed. There's only one possible future consistent with the present. Your decisions, from this perspective, are just complex physical processes in your brain, determined by the laws of physics acting on the current state of your neurons, which was determined by prior states, going back indefinitely. Quantum mechanics introduces randomness, but this doesn't obviously help with free will. Quantum events are probabilistic, not deterministic. When a radioactive atom decays, there's no cause for why it decayed at that particular moment rather than some other. It's genuinely random. If your decisions are influenced by quantum randomness in your brain, they're still not free in any meaningful sense. They're just random. Randomness isn't freedom. A decision influenced by the random outcome of a quantum event is no more your choice than a decision determined by prior causes. Some philosophers and physicists have suggested that quantum randomness might provide a loophole for free will. Perhaps consciousness can somehow select among the possible outcomes of quantum events, collapsing the wave function in a way that reflects genuine choice. This is highly speculative and faces many problems, including the fact that we don't understand what causes wave function collapse, or how consciousness relates to it. But it represents an attempt to find room for free will in quantum mechanics. Neuroscience adds another layer to the problem. Studies have shown that brain activity related to a decision can be detected before the person is consciously aware of making the decision. In famous experiments by Benjamin Libet and others, researchers monitored brain activity while subjects performed simple tasks like pressing a button. They found that a signal called the readiness potential appeared in the brain up to several seconds before subjects reported consciously deciding to act. This suggests the brain begins preparing for an action before we're aware of choosing to perform it. Does this mean we don't actually choose our actions, that the feeling of choice is an after-the-fact rationalization? Critics of this interpretation point out that the readiness potential is statistical, averaging over many trials. It doesn't predict individual decisions with certainty. Moreover, subjects in these experiments can still veto actions at the last moment, suggesting conscious control operates even if unconscious processes initiate action. The interpretation of these experiments remains debated, but they've motivated many neuroscientists and philosophers to question whether free will exists as traditionally conceived. Philosophically, there are several positions on free will. Hard determinism accepts that the universe is deterministic. and concludes that free will doesn't exist. Every action is the inevitable result of prior causes. We're not free in any meaningful sense. The feeling of free will is an illusion generated by our ignorance of the causes of our behaviour. Libertarianism, in the philosophical sense, is the opposite position. It holds that free will exists and that this requires the universe not to be fully deterministic. Some events, particularly human choices, are not determined by prior causes. They're genuinely free, involving a kind of agency that breaks the causal chain. Critics object that this makes free will mysterious and possibly incompatible with science. How can actions be free if they are not caused? Uncaused events seem random, not free. Compatibilism tries to reconcile free will with determinism. It argues that free will and determinism are compatible, that even if our actions are determined, we can still be free in the sense that matters. Freedom doesn't require breaking the causal chain. It requires that your actions result from your desires, beliefs, and character, not from external coercion or compulsion. You're free if you act according to your own will, even if your will is itself determined by prior causes. Compatibilism is popular among philosophers because it seems to preserve the sense in which we ordinarily hold people responsible for their actions. If someone commits a crime because they wanted to, because it flowed from their character and intentions, we consider them responsible. It doesn't matter whether their character was shaped by genes and environment, factors beyond their control. What matters is that the action expressed their will. But critics argue that compatibilism changes the subject. The real question is whether we could have chosen differently. If determinism is true, given exactly the same past and laws of nature, we couldn't have chosen differently. The feeling that we could have is an illusion. Compatibilist freedom isn't the robust metaphysical freedom that our intuitions demand. Recent philosophical work has explored different varieties of free will. Some focus on the role of consciousness in decision-making. Does conscious deliberation play a causal role in our choices, or is it epiphenomenal, a byproduct of brain processes that don't actually influence behaviour? Others examine the relationship between reason responsiveness and freedom. Perhaps what matters is whether you can respond to reasons, whether your beliefs and desires appropriately guide your actions. The neuroscience of decision-making continues to advance. We're learning more about the neural circuits involved in choosing, planning, and executing actions. Different brain regions contribute to different aspects of decision-making. The prefrontal cortex evaluates options and makes decisions. The basal ganglia select actions. The motor cortex executes movements. These systems interact in complex ways, with feedback loops and parallel processing. One finding is that decisions emerge from competition among neural populations representing different options. The option whose neural population reaches a threshold level of activity first wins and is selected. This competition is influenced by many factors: sensory inputs, memories, emotions, goals. The outcome isn't predetermined at the start of deliberation. It depends on how the competition unfolds, which can be influenced by top-down control from prefrontal cortex and other regions. This suggests a picture where decisions are the result of complex dynamic neural processes. These processes are determined by the brain state and the laws governing neural activity. But they're not simple or predictable. Tiny differences in initial conditions can lead to different outcomes. The brain's decision-making machinery is sensitive to many inputs, allowing flexibility and responsiveness. Whether this complexity amounts to free will remains debated. Another relevant line of research concerns the sense of agency, the feeling that you're the cause of your actions. This sense can be manipulated. In experiments, people can be made to feel they caused an event they didn't cause, or to feel they didn't cause an event they did cause. The sense of agency depends on the timing and consistency of sensory feedback, on whether the predicted consequences of an action match what actually happens. This suggests the feeling of free will is constructed by the brain, a model or interpretation rather than direct perception of some metaphysical fact. The debate over free will connects to practical concerns. If free will is an illusion, should we still hold people morally responsible for their actions? Should we punish criminals if they couldn't have chosen differently? Some argue that the absence of free will undermines moral responsibility. We shouldn't blame or punish people for actions they were determined to perform. Others respond that responsibility doesn't require free will in the strong metaphysical sense. Even if actions are determined, we can still distinguish between actions that result from rational deliberation and those that result from coercion, mental illness, or accident. We can hold people responsible as a way of shaping future behaviour, both their own and others. Punishment and reward serve social functions regardless of whether free will exists. There's empirical research on this question. Studies have examined whether believing in free will affects behaviour. Some experiments suggest that people who are encouraged to believe free will is an illusion subsequently behave less morally, cheating more on tests or acting more aggressively. Other studies don't replicate these findings or find the effects as small. The relationship between beliefs about free will and actual behaviour remains unclear. The mystery of free will is unlikely to be resolved soon. It's entangled with other deep mysteries: consciousness, the interpretation of quantum mechanics, the nature of causation and time. Different disciplines bring different perspectives, and there's no agreement on the right way to frame the question, let alone the answer. What's clear is that our intuitive sense of free will, the feeling that we could have chosen differently, is a powerful aspect of conscious experience. Whether this feeling corresponds to a genuine metaphysical property or is a useful illusion constructed by the brain remains one of the most profound questions about human existence. We experience ourselves as agents, as sources of action in the world. Understanding whether this experience reflects reality or illusion touches on the deepest questions about what we are and our place in the causal structure of the universe. We've journeyed through some of the deepest mysteries in science, from the hard problem of consciousness to the dark universe, from the arrow of time to the origin of life, from the Fermi Paradox to the quantum measurement problem, from the mystery of sleep to quantum gravity, from free will to fundamental questions about reality itself. These aren't minor puzzles to be cleared up with more research. They're profound questions that challenge our most basic assumptions about existence. What unites these mysteries is that they lie at the boundaries of human knowledge. Each represents a frontier where our understanding meets its limits, and at these frontiers something remarkable happens. We're forced to question not just what we know, but how we know it, what it means to know something at all. The mysteries push us to develop new concepts, new mathematical frameworks, new experimental techniques. They drive scientific progress not despite being unsolved, but because they remain unsolved. Science has always been a story of solving mysteries only to uncover deeper ones. When Newton developed his laws of motion and gravity, it seemed the universe was understood. But his work led to questions he couldn't answer, questions about the nature of space and time that would require Einstein's relativity to address. When Darwin explained evolution by natural selection, it raised new questions about heredity that would eventually lead to genetics. When physicists developed quantum mechanics, they solved many puzzles about atomic structure and chemical behaviour, but they opened profound questions about measurement, reality, and the nature of the quantum world. Each generation of scientists stands on the shoulders of giants, as Newton famously said. But they also stand at the edge of a great darkness, peering into mysteries their predecessors couldn't have imagined. The solved problems of one era become the foundations for asking questions in the next, and the deepest mysteries often point toward the greatest opportunities for future discovery. Consider what we've learned in just the past few decades. We've discovered thousands of exoplanets, showing that planetary systems are common throughout the galaxy. We've detected gravitational waves, ripples in space-time itself, opening a new window on the universe. We've mapped the human genome, revealing the genetic instructions that make us who we are. We've observed the cosmic microwave background in exquisite detail, learning about the universe's composition and history. We've built quantum computers, devices that exploit superposition and entanglement to process information in fundamentally new ways. Each of these achievements represents progress, but each also highlights how much we still don't understand. Thousands of exoplanets, yet no clear signs of life. Gravitational waves detected, yet no complete theory of quantum gravity. The genome mapped, yet consciousness remains mysterious. The universe's composition measured, yet dark matter and dark energy unexplained. Quantum computers built, yet the measurement problem unsolved. This is the nature of science. Progress reveals new mysteries, even as it solves old ones. The boundary between the known and unknown moves, but it never disappears. There's always more to discover, always deeper questions to ask. This isn't a failure of science, it's a feature. It means the universe is richer and more complex than any finite mind can fully comprehend. What does the future hold? Will we solve these mysteries? Some, perhaps. The Fermi Paradox might be resolved if we detect alien life, or if we colonize space ourselves and find we're alone. Dark matter might be identified if particle physics experiments finally detect the particles that compose it. Quantum gravity might be formulated if string theory or loop quantum gravity or some other approach proves successful. The origin of life might be understood if we create life in the laboratory or find it on other worlds. Consciousness might be explained if neuroscience and philosophy together develop a satisfactory theory of how experience arises from matter. But solving these mysteries will likely reveal new ones. That's the pattern throughout scientific history. What lies beyond the known is not a simple void, but an infinite landscape of further questions. Each answer opens new territories for exploration. This is cause for optimism, not despair. It means science will never be complete, that there will always be frontiers to explore, always mysteries to challenge and inspire us. The mysteries we've discussed tonight also remind us of the value of humility. Science has accomplished extraordinary things, but it hasn't rendered reality transparent. The universe remains deeply strange, full of phenomena we can barely comprehend. Quantum mechanics works, but we don't agree on what it means. General relativity predicts black holes and expanding space-time, but we can't reconcile it with quantum theory. Life exists, but we don't know how it began. We're conscious, but we don't understand how or why. This humility doesn't mean abandoning rationality or embracing mysticism. It means recognizing that our current understanding is incomplete, that the theories we have today are approximations, useful but not final. Future generations will look back on our physics, our biology, our neuroscience, the way we look back on those of our predecessors, with appreciation for genuine insights, but also with recognition of limitations and blind spots. Perhaps most importantly, these mysteries remind us of the value of curiosity, of asking questions without knowing whether we can answer them. The scientists who study consciousness don't know if the hard problem can be solved. Those searching for dark matter don't know if they'll succeed. Those working on quantum gravity have no guarantee their efforts will bear fruit, but they pursue these questions anyway, driven by a desire to understand, by the hope that insight is possible even if not certain. This is the spirit of inquiry that has driven human progress for millennia. From ancient philosophers wondering about the nature of reality to modern scientists probing the mysteries of quantum mechanics and cosmology, humans have always asked deep questions about existence. We may never have all the answers, but the journey of discovery, the process of asking questions and seeking answers, is itself worthwhile. It's what makes us human, what distinguishes us from other species on Earth. So as we conclude this exploration of science's greatest mysteries, let's appreciate both what we know and what we don't. Let's celebrate the progress we've made while acknowledging how far we have yet to go. Let's remain curious, humble, and hopeful. The universe is vast and strange and beautiful, full of wonders we've discovered and mysteries we've yet to solve. Our understanding grows, but the horizon of the unknown grows with it, always receding, always beckoning us forward into new territories of discovery. Thank you for joining me on this journey through the biggest mysteries science still can't solve. If you enjoyed this exploration of the unknown, please like this video and subscribe to Science Sleep Stories for more deep dives into the fascinating world of science. Sweet dreams, and keep wondering about the mysteries that surround us.